Hello, all, and welcome to Artham Academy, aspiring leaders in innovation and technology. In today's video, we will talk about Bernoulli's equation. Now, Bernoulli's equation you would have heard somewhere in your life, whether in your 11th and 12th, whether in your engineering. So, this is one of the most fundamental, basic, and an important equation that everyone should know who has studied fluid mechanics or who is going to study because it holds a specific relevance in the subject and helps your understanding better. So, stay tuned to learn more about Bernoulli's equation.
Bernoulli's equation is quite discussed in the literary events as well as is very important in question solving. If you are in your 11th and 12th or you are in the engineering, you would have heard somewhere about Bernoulli's equation because it's very important and it determines how the flow would be happening and how the velocity, how the pressure, what is the height and all that would be influencing. And in all, it comes to the sum point that it represents the conservation of energy. Its origin can be said as the integrated version of Euler's equation. Euler used the same equation but it was not integrated. Bernoulli moved one step ahead and integrated that equation and presented in front of us so that we can use it and we can satisfy the conservation of energy principle. Now various forces. Following are the forces that acts but varies from case to case and also dependent on the assumptions we consider. These are gravity forces, pressure forces, viscous forces, force due to compressibility, force due to turbulence, and surface tension force. Note that in today's overview we would talk only about the gravity force and the pressure force because in the derivation only those two forces have been considered. And that's why we are discussing forces because I told in the previous slide that it comes in the topic of fluid dynamics, and in dynamics we are concerned more about the forces that are being applied on the fluid. Continuity equation. Before discussing Bernoulli's equation, it's very important that we discuss continuity equation because it's one of the most fundamental equation and it is usually coupled for problem solving with the Bernoulli's equation. It represents mass conservation. So as we can see that continuity represents mass conservation, Bernoulli represents energy conservation. So using that balancing, we try to solve the problem. It helps in the solving problems with Bernoulli's equation. Rho AV is equals to constant. That is what we are assuming here. That is mass is equals to constant. Rho is equals to density of the fluid. A is equals to area of the cross section and V the velocity of the fluid that we have assumed. You can also see in that picture that volume flow over A1, volume flow over A2, then mass, and this is how the whole conservation takes place. That at one section, if some amount of mass is going in, then at the other section, that same amount of mass should come out. And that's very fundamental, right? The mass cannot get lost somewhere. It has to be accumulated, it has to be accounted. And that's how the whole continuity equation works. Before moving to Bernoulli's, let's look at some assumptions as well. So flow is considered on a streamline. The fluid is assumed to be steady. Steady as in it does not change with time. Effect of irreversibilities, viscous forces and friction are not considered because in the previous slide I told you that we are not considering any friction force or the shear force. That's why we are not talking about irreversibilities and viscous forces. The fluid is always treated as incompressible. It means that the density is not changing. So these are the four basic assumptions that we are talking and that we will be using because it sets the boundary so that we do not make any mistakes. Now let's come to the main Bernoulli's equation. It is based on the conservation of energy principle and it's a combination of pressure, velocity and elevation. We can see in the equation P plus rho gh plus half rho v square. It represents energy. Now if we divide by rho g in the complete equation, it becomes in the terms of head. So it's upon us how do we want to use the Bernoulli's equation. As discussed earlier, it's valid for incompressible, steady and non-viscous fluids. So as you can see in your rightwards, there is a pipe that is moving from the Z1 height to Z2 height. So what are the energy changes that are going to happen in the individual components? We are going to look in that the static pressure is going to change, and obviously we are seeing that height is going to change, so how the velocity would react to it. And this is how the whole thing is, that energy would be conserved, but let's look at the points that pressure would be either increased or decreased, or the velocity will either increase or decrease. That is how. Now let's look at the applications. These are the applications you generally find: orifice meter, venturi meter, lift generator, swing of a golf ball, pitted tube, dams and turbines. Orifice meter, venturi meter, they are same almost, because they are used for measuring the flow rate, the discharge. Orifice meter is not that sophisticated, venturi meter is a sophisticated instrument, that's why. But in that also Bernoulli's equation is used to determine the pressure, the velocity and everything. In lift generation, we generally try using the Bernoulli's equation to find how the pressure is less above the wing and the pressure is more below the wing. And that is how we calculate the lift generation. The swing of the ball also happens with that, because of its rotation, a low pressure is created above and high pressure is created down, and that is how it gives a lift and sometimes gives a swing to it. Now talking about pitted tube, it is generally used to find out the velocity of the air through which it's moving, and that's why the Bernoulli's equation is used. In dams and turbines, it does not need any introduction, because if we talk about the Pelton wheel also, there is a huge penstock that comes and there is a height, so we need to calculate what is the velocity when it comes down. So it all happens with the help of Bernoulli's equation. Now where not to use, that is also very important, that you should know that where you can't use Bernoulli's equation: when Mach number is greater than 0.3. Why I'm saying that? Because when the Mach number is greater than 0.3, the fluid tends to become compressible, and for compressible fluids the equation is not valid, because we are assuming density to be constant. When the duct or the pipe is too narrow, when the pipe would be too narrow, the friction would increase a lot. That is FLV square by 2GD, that is the formula that we use. So the friction would increase so much that it would become considerable, and that's why we cannot include in the Bernoulli's equation. In diverging sections of the ducts or the pipe, in the diverging sections, there can be a flow reversal. There can be the pressure that can reduce severely, and that would cause a lot of eddies to come in the pipe, and that will make friction increase again. In the turbulent region, same reason, the frictions would increase a lot. Near the boundary layer also, boundary layer is the region where we see shear forces, where we see a thickening of the fluid, and that's how we can say that there also the friction is in great amount. We can't use the Bernoulli's equation. Also, last but not the least, when the temperature is very significant, values also change of the density, and that's why it no longer remains incompressible but becomes compressible, so we cannot use that. Now some points that you should keep in mind while learning Bernoulli's equation is that it's valid only for inviscid flow, it's valid for incompressible flow, it represents conservation of energy. For rotational fluid, it is valid along the streamline of the fluid and cannot be used when the friction appears in high amount. If you keep these points in your mind while using Bernoulli's equation, I hope that you would never do any mistake.
I hope that you would have loved our video a lot. You can contact Artham Academy for more details if you want, and also to know about the specific courses that you need. Thank you.